Hello, multivariable calculus students. This is Mr. Johnson, and this is the distance formulas for section 9.5. So we're sort of midway in our section here, and what I'd like to do is just take a few moments here to go over three important distance formulas that we'll use for the remainder of this section, but we'll also use this off and on through the remainder of our study of multivariable calculus. So the first one is going to be the distance between a point and a plane, or distance between two parallel planes. This is probably the most common of the three distances because again, it can be used in these two different contexts. Basically, if you have a point in space and a plane and you want to find the distance between the two, and you have two parallel planes, they're similar because all you can do, or all you need to do, is take a single point from maybe a second plane and then just treat it like the same problem. So this formula will work for either of these situations. So let's draw this hypothetical plane in space. Let's say that it looks like this. And on this plane, we're going to identify a point P. And then we're going to identify some point off the plane. Now again, if it's the distance between two parallel planes, this point that I'm notating here, Q, is going to be on the second plane. But if it's simply just a point in space, then we're going to name that Q. And I'm going to go ahead and connect the vector between P and Q. Keep in mind that the vector right now I'm drawing is P to Q. It doesn't actually matter in the end if you go P to Q or Q to P. So if you have two planes, for instance, you just need one point on one plane and one point on the other, and then you can just create the vector however you'd like. Then what we have is a vector that is perpendicular to the plane, and again, all we need is some normal vector to the plane. Don't worry about where the vector is because you can take the vector and move it wherever you'd like it. You just need a vector that is perpendicular or the normal vector to the plane itself. So what I'm going to do is I'm going to notate the important pieces here. So we have P, which is on the plane, and that's just based on what I've written down. Obviously, you can name that whatever you'd like, but I'm just notating each part of the formula. N is the normal vector. Q is the point that's off the plane, or possibly on the second plane. And so our distance now is going to actually be a scalar projection. So I'm going to draw this out so that you understand how these are set up. If you were to take the vector PQ and the vector N, you could sort of pluck them out of space and put them together. You could set them up hypothetically like this, where we have the vector PQ and the vector N like this. And again, I'm just writing them together to just basically connect it to the same picture that we're used to from when we did the projections with the dot product. So if we were to just pluck these vectors out, we don't know what the length is, we don't really care. All we're concerned with is projecting PQ onto N, and we're focused primarily on what this length would be right here. That's the distance we're looking at, because if we're able to line these up in such a way that N points towards Q in the shortest path possible, based on PQ, we're actually going to project PQ onto N. Hypothetically, we're looking at PQ being larger than the length of N, and so we're going to project it onto N, and that way we're going to find our distance. So, maybe even this could be even misleading here with N the way it is. Let me just redraw it for a minute. So let's say that PQ is much larger because, again, N is perpendicular, and let's say N is like this. Okay, now you're going to project PQ down, and we're looking for specifically the distance here of that scalar projection. So that's going to be the distance we're focused on. So we have the component of PQ onto N, which by our formula for the scalar projection is going to be the dot product between the two divided by the magnitude of the normal vector N. So this is your first formula, and again, it's good for the distance between a plane and a point or two parallel planes. Just the key here is to set up everything properly so you have the right points and the right vectors and you stay organized. And then you just perform this operation. Now, depending on how you create the vector PQ, you actually could get a negative value out of this. So take the absolute value of the whole thing, because then that's going to give us the distance that we're searching for. Okay, let's tackle the second one. Now, the second distance that I want to go over is the distance from a point to a line. I think you'll find that this formula is kind of neat, and it connects to some of the stuff we have done already with cross products. So let's go ahead and draw this out. So we have this line in space. We'll name that L. We aren't going to be very creative here. And then we're going to put a point Q that is on this line. Again, these are all dummy variables. Don't be too concerned about that. We will also put a point out here somewhere. Let's call this P. And then we're going to create the vector between them. Now, again, I don't really care. I'm actually going to give you the vector as PQ, but again, it doesn't matter. You could go Q to P. With distance, we're not going to be too concerned about this because we'll just take the absolute value. Also, what we want is the directional vector V. Actually, I'm going to draw this a little bit larger. So this is, again, if you remember back to writing the equation of a line earlier in this section, V is the directional vector made up of A, B, and C. So that's what I'm talking about here, is that it's the slope of that line. Okay, let's create a parallelogram between these two vectors. So we have this shape like this, okay? And what we're focused on is the distance right here. We want that specific distance from Q going basically perpendicular to my line, and analyzing how far P is from the line itself. Okay, so that's what we're shooting for. Now, that particular length is the height of the parallelogram. So let's write out the formula for the parallelogram. Actually, before that, hold on here. Let's do every part of this. So we have Q, which is on the line. We have V, which is the directional vector for our line L. Then we have P, which is a point off the line. And then we have the area of a parallelogram, which is the area of the, or I'm sorry, the length of the base times the height. Okay, now we know from the analysis of cross products that we have already looked at that the area of the parallelogram is the magnitude of the cross product between the vectors that forms the parallelogram. In our case, that is going to be the vector PQ, or QP, again, it doesn't matter, crossed with the vector V. So that is the area of this parallelogram. The base of the parallelogram, the way I've drawn it, is the magnitude of the velocity, or I'm sorry, the vector V, which is the directional vector. The height is what we're trying to find. That's the distance we're searching for. And so we're just going to simply solve for the height. So what we have for our distance is the magnitude of PQ crossed with V divided by the magnitude of V. So here is your second distance formula. I think that one's kind of a neat development. It seems so different than the other one. The other one's a dot product. But again, when you have a plane, you have that normal vector, you're able to kind of position yourself a little bit better. With a line, it's a little hard because if you come up with a perpendicular vector to a line, just try to vision this in space. So if you have a line with a perpendicular vector, that perpendicular vector may not point towards the point in space you're trying to figure out. That's why that's challenging. So that's why what we need to do with a line and a point in space is we need to create this parallelogram shape between the two things so we're able to make sure to analyze the exact distance in the direction of the point. With a plane, the normal vector already positions it well, and that's why we're able to use that guaranteed normal vector. So anyway, those are your two. Now we're going to do the third one. Now the third one is the distance between two skew lines. With this one, you're going to see a lot of similarity to the very first one that we had talked about, the distance between a point and a plane, or the distance between two parallel planes. And you'll see that kind of at the end of this. But let's go ahead and draw this out. And again, this is not going to be easy to do in space, so bear with me. I'm just going to kind of do this generic set. Remember, skew lines do not intersect, and they're not parallel as well. I'm sort of going to draw them looking a bit parallel, but again, I'm not drawing them in space necessarily here, so just pretend like these are two skew lines, okay? On the first one, I'm going to put the point P. On the second one, I'm going to put the point Q, and I'm going to connect those with a vector. So again, you pick any point on one line, any point on the other, and you create vectors between the two. Then I'm going to look at the directional vector v sub 1 from the first line and the directional vector v sub 2 from the second line. And then the last thing that we want just intuitively is that what we need is we need some perpendicular vector that points at the right moment from one skew line to the other one. And the goal is to get that vector pointed at the right moment so we can find the shortest distance between these particular lines. With that said, you can actually see it, I think, a little bit better now than you could in the first distance formula. If we were to take out these two vectors and we had PQ here, and they're already sort of lined up the way I drew them, and you have N here, you're going to project PQ down, a scalar projection, and we're going to focus on the distance right here, which is going to be the shortest distance between these two skew lines. So let's label all of our parts. So we have P on the first line, or on one line. We have Q on the other line. So again, it doesn't matter, just pick one point on one point on the other, and things are good. We have the directional vectors. So v sub 1 and v sub 2 are directional vectors. And then last but not least, we have this vector n, which, like I said, was going to be perpendicular, but it needs to be perpendicular at the right moment and in the right way. It has to point towards the other line. Now, again, if you think back to the cross product, this particular vector is only good if it is perpendicular to both lines, which means we're going to take the cross product between the directional vectors. Okay, so again, this, I warned you, in section 9.4 that the cross product was so pivotal to all the different things that we're going to be looking at next. This is the reason why that idea of the cross product being a creation of a vector that is perpendicular to the vectors involved is going to allow us to guarantee that this vector n is not just perpendicular to the first line, but is also perpendicular to the second line. Okay, so the distance here is going to be another component. It's going to be another scalar projection, and it's going to be the projection of PQ onto n. Again, same as what we really had in the very first definition. And so in the first definition, it was the dot product between the two divided by the magnitude of n. The reason that I wanted to show you this formula, though, the reason I wanted to show you a third formula and make it a little different is because based on the two lines, n is going to be something that we would develop. And so I actually want to show you this formula in terms of the two directional vectors. So we're going to take PQ and we're going to dot it with the cross product between these two vectors. and then we're going to divide it by the magnitude of that cross product. So I'm sort of just representing it a little differently, but I also wanted to make sure you knew where to grab the information from the lines that are provided if it is in fact two skew lines. Now remember, you may get a negative value here, but because we're doing the distance, then we have the absolute value. So this is your third distance formula here. I'll just put it in a box. And those three you want to have close at hand as you work on these problems. Okay, the next video will be on some of the examples pertaining to these distances. Thank you.